Welcome, ladies and gentlemen, to our next part of the electrostatic energy harvest, electrostatic energy conversion. It's the part 3 of this session. I hope you have reviewed the teaching material I have taught in part 1 and part 2. Without review, without reading those materials and practice by yourself, the learning is not complete, and soon you will forget what you have learned here. Not only you need to review the material, you need to do hands-on work. You need to derive the equations by yourself. Then, if you don't understand the fundamental concept between those equations, you need to read the textbooks to find out the meaning behind those equations. After you derive the equations, you need to use the software, the numerical analysis software. For example, MATLAB, Maple, Mathematica, or Fortran, or C++ to analyze those, to use those equations to do analysis to obtain the simulation result. Compare your results to those results in the part 1 and part 2. Then you will learn a lot. Further, you could read the journal materials, the journal papers behind those part 1 and part 2. Read those papers to improve your English comprehension and to push yourself to one step closer to the academia. You may not be a professor in the future, but this way you have your weapons to search for very useful journal publications to help you in your career. Also, not only that, you could also improve your English to show off. Okay, that's part of the good side effect. Now, let's jump to the part 3, electrostatic energy conversion. Again, we emphasize the low frequency operation of the device. Also, we focus the microscale device, because that's one reasoning for electromagnetic and electrostatic energy conversion in the microscale. Given the same size, the electrostatic mechanism can perform better than the electromagnetic mechanism. And also for the fabrication from the viewpoint of the fabrication, electrostatic mechanism device is easier to use the monolithic microfabrication steps to fabricate. But for electromagnetic microfabrication, it could be a bit more complicated, because usually for the CMOS microfabrication process, CMOS process, is not compatible with those magnetic material used in the microelectromagnetic device. So in terms of efficiency and the fabrication, then we might choose to go for electrostatic much better that makes our life easier. This example is a rotary electrostatic energy conversion device. In this figure, the device is a circular device. It's a disk. But in order to explain the concept, we use 1/6 of the full model to explain the operational principle of the device. We have anchors. So this part, and this section are fixed to the wafer. They won't move. They are fixed to the wafer. Then we have this part. This part is suspended by this spring and by the anchor. So the spring supports this solid part. Then if there's a rotary motion, this solid part could move in this way. Easier. The easy moving direction, not easy to move in this radial direction, but easy to move in the circumferential direction. And also, it's not intended for this device to move in this outer plane direction. This is in plane direction. Circumferential and radial directions are in the plane of the wafer. And this is outer plane direction, means out of the wafer plane. Suppose we have charge implanted on this solid part, and we have negative charge on this fixed part. Then you could consider it will have positive charge here, negative charge here. So this part forms a capacitor. Then if this solid part moving in, the overlap area of the capacitor increases. And in this part, the overlap area, if the solid disk moves this way, the overlap area decreases. Then we know the capacitance value equal to permittivity multiplied by overlap area divided by the gap between the two electrodes. Okay, so in this case, in this circumferential moving mode, the gap between two electrodes is fixed, but the overlap area will vary. So in this image, the overlap area for this one reaches its maximum value, and the overlap area between this capacitor reaches its minimum value. So we put C minimum for this capacitor and C maximum for this capacitor. And if the rotary motion is too large, this finger may hit this fixed part to cause damage. Then we design a stopper here. So if the rotary motion is too large, before this part contact this part would contact this part before this one. So the mechanical stopper will protect this device, prevent damage. Also see stopper here. We give them names, fixed combs for them, movable combs for the others, and center ring mass for this, the center. Outer ring frame mass, this one. Middle grid mass, this one. And the rotational motion is indicated by this double arrow line. So stopper here and anchor here. So please familiar yourself with these terminologies in a micro device, like anchors, fixed combs, movable combs, and ladder spring. Because for the spring design, we can have different types of spring design. It could be a straight line. It could be a curved line. It could be like meandering lines. So this one, the ladder type spring, looks like a ladder. You climb the ladder up, then climb the ladder down. The reason for different types of design, because we prefer this outer rim frame mass to move purely in the rotary, the circumferential direction, not in the axial radial direction. See, if there's a radial movement, the gap will be lowered. That's not the intended operation of this device. Then that's the reason we prefer the radial spring constant is large. The circumferential spring constant is small, and the outer plane spring constant should be large to fulfill the intended function of this device. Again, I need to mention this device could be installed in a rotary device, like say the kitchen blender, there's a rotary motion, or the disk in the microwave, there's a rotary motion. Okay, let's jump to the next slide. See, for energy conversion, electrostatic energy conversion, we need to have potential difference between the two electrodes. To provide the potential difference, we could use power supply to have a bias voltage applied to, say, this anchor, and these two anchors are grounded. The other way is to use the electric to implant charge to these fingers to make them become electrics, to carry the charge. Okay, the design goal of this case is to convert kinetic energy from rotational motion. And we need to set the design requirement. The target acceleration, the peak acceleration is 2.5 meters per square second. The resonant frequency is set at 121 Hertz for if this device is going to be installed in a microwave. And we have different acceleration level, resonant frequency for different devices, like washing machine, kitchen blender, or the CD on notebook computer. Next one. So design with a voltage bias. In this way, we need to use power supply to provide the bias voltage to this device. The geometry parameters are important for, say, mechanical engineers. We are entitled to have the detailed design. Then after that, we can do fabrication and to work with electrical engineers to create a system, a commercial product. Some important parameters for you to consider is, see, the gap between the two electrodes, and see the width for the finger, the radius, and initial overlap angle, theta 0. And we have this theta r. The radial, circumferential angle. And the theta is designated as the angular displacement of this movable. So this one is fixed, this one is movable. And we have two capacitors to consider. We have the gap capacitance between this electrode and this electrode. We have overlap capacitance before this surface and between this surface and this surface. So those are the important parameters to be considered for mechanical engineer. Then the modeling issue, those equations for us to help us to analyze the system, to understand the behavior of the system, also to help us to design our device. If everything goes well with the modeling, then we could go to the detailed modeling, then ready for fabrication. The first, total capacitance equal to overlap capacitance plus gap capacitance. And the overlap capacitance, C, equal to the dielectric constant multiplied by the overlap area divided by the gap. So they define this equation. T is the thickness, and theta 0, initial angle, overlap angle, and theta is the displacement. And A of n is a function of these geometry parameters. R1, WF, G. You could figure this out by setting I equal to 1, or from I equal to 1. I equal to 1 and n equal to 1. Say only one set of the finger, and you could write this equation out to convince yourself. Then you could increase this n number to 2, 3. Then just have then to help yourself or to convince yourself this equation is correct. But we won't do that in a class. It's time consuming, and you should have something to do by yourself to exercise, mental exercise. Okay, so this is the gap capacitance, epsilon times T times this function B of n with this expression. Okay, the expression here Again, you are encouraged to write down the expression, and you can assume the number n equal to 1 or 2 to convince yourself this is correct, or to prove they are wrong, either way, because not everything is correct, like written in a journal paper. So if there's a mistake, then you should be happy, because you have the ability to evaluate other people's work. Then the spring design. Remember I mentioned it's important to have a large radial spring constant, small circumferential spring constant, large outer plane spring constant. Why spring constant? Remember the Hooke's law. For any spring, we say within the small deformation, we have the Hooke's law to analyze a spring. The Hooke's law says external force equals spring constant multiplied by the displacement. We use the symbol F equal to K multiplied by X. The spring constant K is an indicator to indicate the difficulty to extend the spring. If K is very large, then it's not easy to elongate or shorten the spring. Contrarily, if spring constant is small, means it takes some very little effort to elongate or compress, shorten the spring. Okay, so they have Kr, radial spring constant, and rotational spring constant, K theta, and outer plane spring constant, Kz. So the purpose is that Kr should be small, but Kz and K theta, Kz and Kr should be large. In this investigation, the authors come up with 3 types of spring design. See, for this one, serpentine, the meandering type design, the 90-degree angle design. This is the traditional design used in the micro device. Then you could twist a little bit. So you could change the angle from 90 degree to less than 90 degree to see what happens. Then you could also add one more step. Then this one looks like a ladder or step, step. You can climb the ladder. Then here we have red ink numbers to indicate the dimensions of the 3 designs. Then see, we have Kr over K theta, Kz over Kr, Kz over K theta. Remember, Kr should be large, K theta should be small, 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 and large, large. So these 2 numbers should be large, and this one is for reference. So large, okay, so this one, we have the largest value. And this one, large. In this case, we have the largest value. And for this value, they are comparable. So based on this table, they choose to use the ladder type design for their device. Then we could use the mechanics of material to derive the spring constant values, the spring constant expressions, we could use energy method to do that. Because the Bernoulli bending theory, the simple ones, are not enough to derive the spring constant for these a little bit complicated beams. So we can use the energy method, like unit load method, or like virtual energy, potential energy method to derive the equations. But the convenient way is to use finite element analysis. If the goal is not to do a very fundamental mechanics investigation, we could resolve to finite element analysis to calculate the spring constant values. Okay, in this case, the authors use the finite element analysis to do that. And also, the resonance frequency is an important issue for operation of the commercial device, because we prefer the device to operate in the frequency range much lower than the resonance frequency. Or in some cases, we prefer the device to operate near its resonance frequency. For energy conversion device, to operate the device near its resonance frequency might be a good choice, because during resonance we have very violent, large vibration amplitude, which could help to convert, to harvest a large amount of vibration energy, to turn it into electrical energy. Okay, so we use finite element analysis to obtain the resonance frequency of the device. So in this figure, the blue part means during resonance, small vibration, small displacement, and the red part, we have large vibrations. So, yeah, the vibration, in this vibration mode, yeah, the mode is like rotational motion, the resonance. So the resonance frequency is nearly 67 Hertz. So, yeah, that's a good number for designers to remember or to make use of it. Then the fabrication process. In this process, they use SOI wafer, like silicon on insulator, Si, silicon dioxide. That's why it has the name SOI, silicon on insulator. So to begin with, a 3 micro SOI wafer means in the device there, the thickness of the silicon is 30 micron. Then they deposit aluminum on the silicon. Then they use PECVD, the chemical vapor deposition, to deposit silicon glass. Silicon glass there. They could be used later for a mask for etching purpose. Then they pattern the silicon glass they use RIE to pattern the silicon glass. Then use DRIE, deep reactive ion etching. They use ions to bombard the surface, and they could attack the parts without protection of the silicon glass. So in this way, they use deep reactive ion etching to create the springs, combs, and proof mass. Then they use the HF vapor to remove the silicon dioxide. Then the device now can move. Okay. Again, if you are curious about this PECVD, DRIE, RIE, and all these things, HF vapor for release, you are encouraged to study the microfabrication textbook to find out those like detailed description of these microfabrication processes. But we won't go to the detail in this class. Those are not the focus of this class. Okay, so to evaluate or to take a look at the micro device, we need to use microscope. In order to have very clear view, very high magnification ratio, we could resort to scanning electron microscope, SEM, to have a very sharp, high contrast, high magnification ratio photo. So this is the SEM photo of the fabricated device. See, we have the ladder spring, we have the anchor, and the fixed combs, and the movable combs. Then the center circular disc. See, fixed combs here, and center ring mass. Stopper to prevent damage or to protect the device. Movable combs, see, they are very thin and long, so very easy to be damaged once there's a collision between the movable combs and the fixed combs. Another thing we need to mention is we need to have many etching holes on the large surface area. Remember, we have this process. Use HF vapor to release the microstructure. In order to remove the silicon dioxide, if there's no holes here, then the HF gas is not easy, vapor is not easy to go under and remove the silicon dioxide. So it's better to have all these holes for HF vapor to get in and attack the silicon dioxide to remove them. So that's the whole purpose of all these tiny holes to help release. See, all these tiny holes help to release the surface, the structure with large surface area. And for SEM photo, we have a scale bar, 100 micrometer, and we need to have the high voltage input, 5 kilovolt, because we use electrons as the medium to take the photo. Okay. The SEM photos with much higher magnifications, the center rim, the ladder, the stopper, and see the columns. You can see the gap clearly. After fabrication, we need to test the device. It's important to know these measurement techniques and what kind of equipment we could use for experiment. So I will spend time to explain to you all these details to help you to enter this energy conversion mechanism world. Okay, remember we use the DC power supply to provide the DC bias to this energy conversion device. Okay, we have the shaker to create the relative motion or the rotary motion of the moving part. Then, in order to know the acceleration of the shaker, we use accelerometer sensor to monitor the acceleration of the shaker. So we use data acquisition board to collect the data to the computer. And for the, remember, charge redistributes itself in the wire, in the electrode, to have the current. So we have because the charge generated is small, so we need to have the charge amplifier to amplify the charge. Then send the signal to dynamic signal analyzer to collect the data. But the shaker, we use the signal analyzer to provide the signal. But we need to amplify the signal to drive the shaker. Okay, so the signal data, analyzer data, could be fed into the computer to analyze the data. Okay, so this is the block diagram of the experimental setup. Okay, then for the electrostatic energy conversion. So this is the typical curve for the energy conversion electrostatic mechanism. We have charge Q in the y coordinate. We have voltage V in the x coordinate. For capacitor, Q equals capacitance multiplied by voltage. Then, so the slope here represents the capacitance. So for the operation, we could use the DC power supply to charge the device to provide the charge to the electrode. After that, we could turn off the power supply. Then the charge is fixed. Then if there is a rotary motion, then the capacitance will be varied. So from the maximum value, like 100% overlap, to the minimum overlap. So we have the small slope is the small capacitance. So rotary motion, maximum overlap to minimum overlap. See, then the charge dropped to say 0 again. Then we turn on the power supply to provide the charge. Then turn off power supply and rotary motion from minimum to maximum. From maximum overlap to minimum overlap. Then just keep this circle, keep going. So in this QV curve, the curve from A, B to C means we store energy to the capacitor. And from D back to A, we return the energy, this section of energy, back to the environment. So this surface, this area enclosed by the line A, B, BD, and DA are the stored energy after each cycle of operation. Okay, we use this C mains to represent the capacitance of the mains device. We have this varying sign. So for this operation, say without periodic capacitance, we use the geometry argument. We could have this expression. So you are encouraged to derive this expression by yourself. So it's important to do the derivations to help yourself to understand if you could follow me, then we could manipulate this equation to have this one. So V maxima means this voltage, V minimum or V start means this one, and C maximum slope this one, C minimum slope this one. We could add the periodic capacitance to the equations to make it more realistic. Then this one is the energy stored in one cycle. Again, you could use geometry algebra to derive this one. You are also encouraged to derive this one by yourself. Okay, we could turn this one into this one. Okay, the device here, they should be packaged. Then we could use wire bonding, use gold wire to get a signal out to this package. Or we could have this metal cap to change the gas pressure or the air pressure in the package. Low pressure or near vacuum, the quality factor of the system will be high to decrease energy dissipation. Okay, then we need to have the circuit to move the stored energy in the C mains to the storage capacitor, and they could use to run the node to provide the energy to our load, the device RL. So originally switch 1 should be closed to provide the energy. After that, switch 1 should open. Then SW3 should be closed. Then we could use the dynamic signal analyzer to get the signal. So after that, this SW2 can close and to transfer the charge to the storage. Then SW2 could open again, then storage current. The charge can go through the RL to drive the load. So this is ground. So you could go ahead and find out this journal paper and to get to read the detail of this circuit. Although you are a mechanical engineer, if you have research interest in this microsensor or the energy conversion device, you are encouraged to get yourself too familiar with some simple electronics. It's fun to expand your knowledge, to equip yourself with a high potential, to have a versatile career possibilities. Then we have the result, the frequency, and this is capacitance change. See, at near the resonant frequency, we have very high capacitance change. Capacitance change is desired because they would increase the energy stored. So see, that's the point why it is important to have the ability to do the theory analysis. See, because of this analysis, we know if C max minus C minimum is large, we could have large energy stored. Then C maximum minus C minimum is the capacitance change. So we would like to have very large of capacitance change at the operational frequency. See here, capacitance change and frequency. Then you will have a clear picture in your mind. This is why it's important to understand the theory, the equations, and to compare with, then it could be used to compare with the experiments and to guide us to create or to do the experiments. In reality, that's what we need to have high capacitance change. Then this is resistance and power, output power. Remember, to have the maximum output power, we need to match the impedance of the load to the output impedance of the energy conversion device. So near 80 mega ohm, you have the maximum power transfer. Okay, the authors selected 1 volt power supply, DC power supply, to provide the bias voltage needed to operate their device. Then they observed capacitance change at 110 Hertz. And the maximum capacitance, C, 2 and 8 picofaraday for vibrations at 0.5 G and 2.5 G. See, these accelerations are those kitchen blenders or microwave rotary disk, the accelerations of those devices. Okay. They use LCR meter to measure the impedance of the mains variable capacitor without vibration. And also the measured parallel periodic resistance is about 80 mega ohm. The parallel resistance. There are various models for the capacitor, and they have parallel series, different models. And in this case, we select a parallel model to measure the impedance of the device. The capacitor C. Okay, output power as a function of the loading resistance with different acceleration levels. See, if we increase the acceleration, then the output power increases from the lowest to the highest. Then we have a model for the capacitance variation, but we also need to have a model for mechanical vibration. See, in this model, we have mechanical vibration, we have electronic circuit, and there's an interface between them. The interface is the electrostatic force. So the electrostatic force equal to the electrostatic potential differentiation with respect to the displacement. So we could derive the expression for electric potential and do the differentiation to find out this electrostatic force. So the result is this one. It's a function of Z. And also we have the charge Q and C0 initial capacitance. And Z is the overlap displacement. And X0 is the initial gap overlap. And the C0, we have N gaps. The number of gaps is N. And dielectric constant, thickness. And G is the gap. So here are the electrical damping force. So we need this one to couple it with the mechanical model. Okay, so that would conclude our part 3 of this electrostatic energy conversion. Thank you for your attendance. And you are, again, encouraged to read the paper by yourself. You could try to derive the equations we derived and review all the material. Do the analysis, get the results, simulation result. They would help you a lot. Also, it's fun, isn't it? Okay, so thank you. I'll see you next time.